Rising sea levels and sinking lands, two forces reshaping our world's coastlines. In the Mississippi Delta, land subsidence has become a critical issue, threatening ecosystems, communities, and infrastructures. But what causes this sinking, and how can we measure it? Join us as we explore groundbreaking research from Louisiana's Subsidence Superstation, where advanced technology uncovers the hidden mechanisms driving land loss in river deltas. From surface compaction to deep layer deformation, this study reveals surprising insights into the future of our coastal landscape.
Good day, everyone. I will be discussing a journal article entitled Novel Integration of Geodetic and Geologic Methods for High-Resolution Monitoring of Subsidence in the Mississippi Delta. The paper proposes strategies to mitigate climate change impacts on vulnerable coastal lowlands and river deltas facing inundation. For the table of contents, I will be discussing these parts of the paper, which are the introduction, environmental setting, instrumentation, long-term results from the optical fiber sensors, GPS results, RSET-MH results, synthesis and implications, information S1, and conclusions. To start, it's important to highlight that coastal lowlands and river deltas, which are typically less than 10 meters above sea level, are particularly vulnerable to the impacts of climate change. This includes threats such as rising sea levels and increasing severe tropical storm surge. Furthermore, many large deltas are facing a significant challenge. They are receiving insufficient sediment. This lack of sediment is crucial for maintaining the integrity of these landforms. Alarmingly, in many cases, the rates of subsidence in areas can exceed the rate of sea level rise, leading to heightened risk of flooding and dam loss. There is a pressing need to better understand the various factors that contribute to coastal subsidence. Recent research efforts have encountered difficulties due to conflicting results from different measurements techniques, which complicates the researchers' ability to identify the true drivers of subsidence. The study of the researchers specifically focuses on the Mississippi Delta, where they have established a novel subsidence superstation. The superstation aims to integrate multiple monitoring methods at a single site, which allow them to provide more precise measurement of sediment compaction and subsidence. This approach addresses the limitation of previous studies that often relied on isolated techniques. Lastly, the superstation is strategically located near the planned mid-Barataria sediment diversion. This diversion is expected to significantly influence sediment deposition and compaction rates in the region, making their research particularly relevant for understanding future subsidence dynamics. For the environmental setting, the subsidence superstation is positioned in brackish marsh environment approximately 2 meters from the bank of Mississippi River. This location is significant as it allows the researchers to study the interaction between the river and marsh ecosystem. To support their research, they utilize data from Coastwide Reference Monitoring System Installation 0276. This site records essential hydrological data relevant to marsh environment, including water height and other critical parameters that influence subsidence and sediment dynamics in the area. To gain insights into subsurface conditions, they drilled three boreholes at the site. These boreholes are crucial for studying the stratigraphy beneath the marsh surface. The shallow stratigraphy includes superficial pit bed, which is vital for carbon storage and habitat provision, and overbank deposits from Mississippi River, which contribute to the sediment processes. For instrumentation, the optical fiber strain meter is composed of a thin cable that houses two optical fibers. This design is crucial for measuring strain accurately in the subsurface environment. The cable is specifically tensioned to stretch the optical fibers beyond the expected negative strain, ensuring that any changes in strain can be detected effectively. The primary function of optical fiber strain meter is monitor changes in the length of the optical fiber caused by displacement of the borehole. This is achieved through an interferometric tracking system which allows the precise measurements of strain as the boreholes experiences movements. The data collected from the optical fiber strain meter undergoes rigorous processing. This includes temperature corrections to account for any variations that may affect the optical length of the fibers. By correcting the temperature fluctuations, they can ensure that the strain measurements are accurate and reliable. An essential feature of their instrumentation is the capability of real-time data streaming. The processed data is streamed to a data server, allowing for near instantaneous examination and recording of the strain measurements. This is the illustration of the instruments installed at the subsidence superstation, and this is the stratigraphy they gathered using the subsidence superstation they planted in the Mississippi River. For the long-term results from the optical fiber sensors, all three optical fibers sensors demonstrated a clear annual cycle that correlates with local marsh water height. This cyclical pattern indicates the sensor's sensitivity to environmental changes. Over the course of the 5-year experiment, they observed that the compaction of the material surrounding the strain meter array reached approximately 1 mm. It is important that the gaps encountered were primarily due to power outages and sensor malfunctions that occurred during significant hurricanes. These interruptions affected the continuity of the data collection and analysis. The uncertainty in the calculated compaction rates is influenced by the aforementioned data gaps, as well as issues related to temperature compensation in one of the sensors. For the GPS results, the GPS data were analyzed from August 2016 to August 2021 at three different stations: MGW1, MGW2, and MGW3. This extensive time frame allows the comprehensive understanding of subsidence trends in the region. To ensure the accuracy of the measurements, ocean tide loading corrections were computed using FES 2014b model. The researchers employed a multi-channel singular spectrum analysis method to estimate secular trends in the data. This technique effectively removes seasonal oscillations from the GPS time series, allowing them to focus on long-term trends in subsidence. The analysis revealed that the average subsidence rate across all three stations is determined to be 2.5 plus or minus 0.3 millimeter per year. This finding is significant as it provides a quantifiable measure of land movement in the Mississippi Delta, which is critical for understanding the region's vulnerability to sea level rise and other environmental changes. For the RSET-MH results, the RSET-MH method determines shallow subsidence by comparing surface elevation change with vertical accretion. This comparison allows them to assess how much the land is sinking relative to the amount of the sediment being added to the surface over time. Recent analysis indicate an increase in shallow subsidence rates from 2015 to 2021. This trend is significant as it suggests that the dynamics of flood movements in the region are changing, potentially influenced by environmental factors such as sediment deposition from events like Hurricane Isaac. All four marker horizon records analyzed showed that the vertical accretion rates are consistently higher than the rates of surface elevation change. This discrepancy indicates that while sediment is being added to the surface, the land is not rising at the same rate, leading to increased subsidence. Interestingly, the compaction rates observed in deeper layers are lower than what was predicted by geotechnical modeling studies. This finding suggests that actual compaction occurring in the subsurface may be less severe than previously thought, which has implications for future modeling and understanding of subsidence processes in the area. For the synthesis and implications, it is well established that Holocene sediment compaction plays a significant role in contributing to subsidence in coastal Louisiana. This compaction primarily occurs in the upper layers of Holocene sediments, which are subject to loading and pressure changes over time. One critical observation is that GPS measurements often overlook the effects of compaction in the upper Holocene sediments. Many GPS instruments are anchored deeper, which means they do not capture the full extent of shallow subsidence caused by sediment compaction. Looking ahead, the implementation of sediment diversion, such as the Mid-Barataria Sediment Diversion Project, may significantly alter current subsidence rates in the superstation area. These diversions are expected to increase sediment input, which could lead to changes in compaction dynamics and overall land stability. To enhance the researchers' understanding and predictions of coastal subsidence, it is essential to employ integrated measurements and models. The combination of various monitoring techniques, such as GPS and strain meters, allows for a more comprehensive assessment of both shallow and deep subsidence processes. This integrated approach is crucial for developing robust predictions regarding future subsidence and its implications for coastal management. For the information S1, the GPS antennas and optical fiber strain meters are anchored at the depth of 1.3 meters. This depth allows for the detection of deformation occurring below this level, ensuring that the instruments can effectively monitor subsidence in the region. The solar-powered strain sensors are designed to operate with approximately 5 watts of power. This energy is essential not only for the functioning of the sensors, but also for the transmission of data to a central server. The use of solar power is particularly advantageous in remote locations where traditional power sources may be unavailable. One of the challenges faced during the operations of these instruments is data interruptions, which can lead to gaps in the records. These gaps complicate the analysis of displacement records as there is no way to recover the displacement that accumulates during the unpowered periods. The data editing process involves aligning the records before and after the gaps, which can introduce uncertainties in the analysis. For the conclusions of this paper, the combination of optical fiber strain meters and GPS has allowed the researchers to capture detailed subsidence records, enhancing the understanding of the dynamics at play in this vulnerable region. This approach is particularly novel as it leverages the strength of both methods to monitor subsidence more effectively than traditional techniques alone. The strain meters reveal micron-level displacement, which is crucial for understanding the subsidence processes occurring at various depths. This sensitivity enables the researchers to discern subtle changes that may be overlooked with less precise instruments, thereby providing a clearer picture of subsidence mechanisms at work. The findings of researchers indicate that the compaction of Holocene deposits is minimal, measuring less than 0.25 plus or minus 0.27 millimeter per year. This suggests that the observed subsidence is primarily driven by deeper geological processes rather than compaction of the upper layers. Looking ahead, the potential for the new sediment deposition in the region, particularly from projects like the Mid-Barataria sediment diversion, may significantly influence compaction rates and subsidence dynamics. This could alter the current understanding of subsidence processes and necessitate further investigation into how these changes will impact the marsh ecosystem. And that's all for this video. Thank you for your time and attention. Thank you for watching. Bye!